Okay, guys. Hi. Just before we get started, just a couple reminders. Yep. Hi. Let me remind you, I'm looking for someone to be the class rep for this class. So if you're interested, please send me an email. I'm like part of the way done marking assignment 2. So I should be done today, later today. So look out for that. I did want to mention just a quick example about assignment 2. And then then we're going to move on. Well, I think it's like the fun part of this class is defining the natural numbers. Okay. But first, so let's see. So today, first, like a quick note about assignment 2. And then we'll talk about the natural numbers. Okay. And our plan is that starting from the sets, we have to define in a concrete way, like, and not only that, but we have to show that they, like all the properties we normally expect of natural numbers hold for these ones we construct. You know, basically we have to show that the things we just construct deserve the name natural numbers. Okay. So first, a quick note about assignment 2. Just to do a little bit of an example. To kind of add on to a quick example, going to have f and g. These are going to be two one-to-one functions. Maybe f sends 1 to A, f sends 2 to B, f sends 3 to C. This is a one-to-one function. It has an inverse, all that nice stuff. Okay, what about G? G is going to send A to alpha. G is going to send B to beta, and G is going to send D to delta. Okay. And so we can construct f of G, we can construct f inverse, we can construct G inverse, and so on. Okay, so f inverse, well, that's just A1, B2. Right? And notice if I compose f with f inverse, well, that is a function. So f inverse sends A to 1, and then f sends 1 back to A. So that is a function AA, BB, CC. That's the identity on the set A where A equals ABC. And A is also, you can write it as the domain of F. Okay, so F composed with F that should be the, so F of F inverse is the identity on the range of F. Similarly, F inverse of F is the identity on the domain of F. Okay, just as an example. Now we can do f of g. What is f of g? Or do I think I want to do g of f. I'm sorry. G of f. What is g of f? Well, 1 gets sent to A and A gets sent to alpha. So g of f sends 1 to alpha. And g of f sends 2 to beta. And g of f doesn't do anything to 3 or anything else. So that's it for g of f. So because f and g were one-to-one, so is g of f and g of f inverse. That's just alpha 1 beta 2. And you can check that that is the same as F inverse of G inverse, just like in, but when I compute G of F inverse composed with G of F, this is just the function. So this is a function when it sends 1 to alpha and then alpha to 1. This is this function, which is the identity on the domain of F. The identity on A prime, not the domain of F. Okay. And I just wanted to do this example to show you that, just to remind you that when you compose two functions, the domain of G of F might be smaller than the domain of F. And the reason is that G of F is not defined at 3. Okay. And this is just an example of something that happens when when you don't require, just remember, we don't require that the domain, is contained in the domain of G. Okay. In fact, I guess you could come up with a situation where you compose two functions and the result is just like the empty set, but it's okay. So if you, I guess it just goes to show you why do we normally we might require that in order to form G of F, you need that the range of F is contained in the domain of G. So, and why do we require that? So that like this weird stuff doesn't happen where you compose two functions and you get a smaller domain. Okay, if you make this, if you always assume that if you don't allow to compose functions unless they satisfy this property, then you don't have to worry about stuff like this. We do not require that for this class, so we do have to worry about stuff like this. Okay. Now I wanted to start talking about the natural numbers. Okay. So we need the natural numbers. So our plan is we want to construct some sets with control numbers, and we want our model to satisfy certain properties, like just the can someone please tell me some axioms? Okay. Yeah, there are, you could say, there's another, we'll start with that. There's another way to interpret what you said, which is to say, for all n, there exists M bigger than N. That's another way to say it. Let's see. You know, there's a lot of them. There's a lot of rules of arithmetic that we use all the time. Another one might be like the commutative property. Can also say like for all N, there exists, you know, like N plus 1. Many, many others. Would be a principle of mathematical induction. Many more. Okay, so what we have is we have a bunch of axioms. So one option is to take those axioms of sets and just hope that they don't contradict each other. Hope for the best. Okay. Okay, and that is normally what we do, but this class is called set theory, so that's not good enough, at least in this class. Okay. In this class, we want all these things to be true, but we don't want to introduce anything that we don't need to build up the natural numbers and all these different properties from sets. Okay. We'll need to introduce, I think, at least one more axiom on sets to get this property. We need a new axiom. But other than that, we can get pretty much everything. Okay. And the trick is that if I ask you to construct a set, just starting from the axioms, there's like not much you can do. The first thing you can construct would be the empty set. Okay. So let's just make that a number. So define 0 to just be the empty set. Okay. This is kind of the simplistic, one of the simplest examples of a set. So I guess that's good that it should correspond to a simple natural number. Not only that, you'll notice that, so we can kind of think of the set 0 Oh, do we take 0 as a natural number for this course? Yes. Okay. So yeah, so 0 is going to be our kind of our starting point for the natural numbers. Well, that is because it's kind of the starting point for sets as well. Okay, and not only that, the number of elements of the empty set is 0. So like the empty set is its own label for the number of elements of the empty set. Okay. And then what we do a trick that X be any set, and we define the successor of X to be X union the singleton of X. Of course, we should be a little bit careful. Let's at least establish that this is a set, at least briefly. Notice if X is a set, then the singleton of X is a set. So the union of the singleton of X with X is also a set. Okay. So we can take the successor of any set, but we really only want to do it when X is a natural number. Okay. So what we do now is we start from 0 and we define S of 0 to be 1. That just means take 0 union with a singleton containing 0. Well, remembering that 0 is a set and the singleton is also a set, this is the empty set union the singleton of the empty set, which is just the singleton. Okay, so now notice 1 is a set which has 1 element. Okay, that will be useful for us. Okay. And then we just keep on going. We take 1 and find the successor of 1 is just 2. Oops, successor of 1. So that's just 1 union the singleton containing 1. Okay. And now notice again, 2 is a set and 2 has 2 things in it. The 2 things in 2, well, those are just the natural numbers that come before 2. Okay, then we just keep on adding 1. 3, what's that? Well, that's just a successor of 2. Two is the set 0, 1. Okay, so 3 is a set with 3 elements. Okay. I mean, just keep on going. Okay. So instead of, so kind of this function s start with 0. The next one is the next number is 1, the successor of 0. The next, and the successor of 2 is the next number after. Okay. So let's also have another bit of notation. Instead of s of x, we'll just define x plus 1. So that means like the definition of 3 is that it's just the number after 2 is just 2 plus 1. Okay. But notice that I have not defined one more or the next natural number. Okay, and so what we want is process indefinitely and gather up all the things you get and call that the natural numbers. Okay, so here's like a plan. Start with 0 and then do the next one after 0 is 1, the next going forever and ever, and call that the natural numbers. And then we want to prove things about the natural numbers. So we want to define like 3 plus 5 equals 8 and whatever. Okay. But now you should be like, there's something I've kind of cheated. That is, I've cheated by putting these dots. In another class, I would just ignore this and say it's fine. We can ignore this kind of thing in every other class, but this class. Okay. So, we need a way to kind of rigorously be able to put in these dots. Okay, so that means we need like an axiom to solve things for us. We need to talk about what is it we want from the natural numbers. Well, it turns out one of the first things we want is, in other words, we want the well ordering principle. Okay, another way to state that is that we want n to satisfy that 0 is a natural number, and we want n to be that if n is a natural number, then n plus 1 is a natural number. And then we also want n, the set of all natural numbers, to be the smallest 1 and 2. And the reason for this third property is that this is essentially the principle of mathematical induction. Let S be a subset of natural numbers, which is non-empty. And if n is in S and n plus 1 is in S, then S has the least element. No, I don't want to. No. I want 0 to be in S. Yes. Okay. So if I which has 0 and has, if n is in S and n plus 1, S is equal to n. And another way to state this is that if P of 0 and P of n implies P of n plus 1, then P of n for all n. Okay. Okay, so sets which satisfy this property are important, and we give them a special name. And then after I tell you what the name of those sets are, we'll take a break. So we just have the definition. Let S be a set. S is called inductive if 0 is an element of S, and then for all n plus 1 is also in S. Okay, so let us now take a break for about 5 minutes. Okay, see you guys soon.